Hi, I'm Dr. Jeff Groh, and this is Differential Equations. Before discussing what a differential equation is, I find it useful to discuss what an equation is. Consider the expression b squared minus 4ac. Is this an equation? The answer is no. This is not an equation because it doesn't have an equal sign. Equations are two expressions separated by an equal sign. In order to be an equation, you must have an equal sign. Consider now the following equation: x plus x equals 2x. For what values of x is this equation true? The answer is, this equation is true for all values of x. Such an equation is called an identity. An identity is an equation that is true for all replacements of the variable. Consider the equation 2x plus 3 equals 0. For what values of x is this equation true? This equation is true only when x is negative 3/2, and it's not true for any other value of x. An equation that is true for some replacements of the variable, but not for all, is called a conditional equation. There is yet a third kind of equation. For what values of x is this equation true? This equation is not true for any replacements of the variable. There are no values of x that you can substitute that results in a true statement. Such an equation is called a contradiction. A contradiction is an equation that is not true for any replacements of the variable. Now that we know what an equation is, we're ready to define what we mean by a differential equation. A differential equation is an equation involving one or more derivatives of an unknown function. As an example, consider the differential equation dp dt equals kp, an equation that is sometimes called the natural growth law or the Malthusian growth law, after Malthus, who in the 18th century predicted the end of the world based on this equation. This equation says that the rate of growth of a function, dp dt, is proportional to the population size. This is a reasonable hypothesis if you consider that if we were to lock 1,000 people into a building and give them everything they needed to survive over the course of a decade, at the end of that decade, would we still have 1,000 people? Probably not. It really depends upon how well they like each other, though. If they like each other a lot, you might end up with more than 1,000 people at the end of the decade. Similarly, if you lock 1,000,000 people into a big city and keep them there with everything that they need to survive over the course of a decade, at the end of that decade, will you still have only 1,000,000 people, or will you have more? In all likelihood, you'll have quite a few more, and you'll have proportionally more than the 1,000 that you locked into the building over the same decade. As you can see, the rate of growth of the population will depend upon how big the population is. Now, this differential equation doesn't tell us what the function p is, the population size. To solve for that, we can separate the variables by multiplying dt to the right and dividing p to the left. Once we have separated the variables in this way, we can integrate both sides. When we integrate, we get the natural log of the absolute value of p plus an arbitrary constant is equal to kt plus another arbitrary constant. Note, we can combine the two arbitrary constants together, yielding the natural log of the absolute value of p is kt plus another arbitrary constant. The difference of two arbitrary constants being an arbitrary constant. Now, to solve an equation like this for p, we have to whittle away at the things surrounding p, starting with the thing that's furthest away by the order of operations agreement, in particular with the natural log function. You also use opposite operations, and the opposite of the natural log is the exponential function e to the power of. When we take e to the power of each side, we get the absolute value of p is e to the kt times e to the c3. So we have the absolute value of p is e to the kt times, we said e to the c3, but that's going to be some constant c4, where c4 lives in the set of positive real numbers. C4 is an element of, this is the symbol that means an element of. A blackboard bold R refers to the set of real numbers, and a superscript of plus means positive real numbers. After all, C4 was e to the power of C3, and the exponential function only outputs non-negative values. To solve an absolute value equation, provided a is positive, the solution is x equals plus or minus a, both positive and negative values. So for us, p is plus or minus e to the kt times c4. We could write the c4 in the front because of the commutative law of multiplication. Plus or minus c4 allows for the c4 with the plus or minus to be either a positive constant or a negative constant. We may as well write p is equal to c5 e to the kt, where c5 is an arbitrary real number, with 0 giving a valid solution to the original differential equation. Now, we've been careful making distinctions between each of the arbitrary constants in this particular derivation. However, in the future, we're just going to call all of these constants C, allowing for an abusive notation. Even though they do represent different constants, we're going to allow convention, which just calls them all C. So it turns out that the differential equation dp dt equals kp has solutions. P is an arbitrary constant times e to the kt. In other words, we get more than one solution. We get what is called a one-parameter family of solutions, the constant c, the constant of integration being that parameter. Now, this one-parameter family of solutions for different values of c gives you different exponential solution curves. The constant 0 is also a solution, and if you choose c to be negative, the solutions will work this way as well. Now, it would be nice to know that the population of the Earth grows on a particular curve, but there are infinitely many curves that solve this differential equation. To nail down one, you need one additional piece of information. In particular, you need to know maybe one point, P0, that the curve goes through. If you specify that one point, then you can pick out the one curve that solves the differential equation together with this piece of data, which is called an initial condition. Whenever we specify the value of the function at some particular point. This is called an initial condition. Whenever you have a differential equation together with an initial condition, you have what is called an initial value problem, or IVP. The hope is that by specifying one particular point that the solution curve passes through, you can pick out the one solution to the differential equation that also satisfies this initial data. To summarize, we don't expect there to be only one solution to a differential equation. We expect there to be a one-parameter family of solutions because there should be some constant of integration. In order to undo a derivative, you have to integrate. And when you integrate, you get an arbitrary constant. So you get a one-parameter family of solutions. In order to specify one particular solution, you have to specify some point that the solution curve passes through, called initial data, or just sometimes data. So let me review. A differential equation is an equation involving an independent variable, a dependent variable y, some unknown function, and one or more of its derivatives. That is a general differential equation. The highest order derivative that appears in a differential equation is called the order of the differential equation. So the order of a DE, a differential equation, is the highest order derivative that appears in the equation. So, for example, consider the equation y double prime plus 2 over xy prime plus y equals 0. The highest order derivative that appears on the unknown function y is 2, and therefore this is a second order differential equation. Similarly, in the differential equation y prime quantity squared equals a over y minus k, the highest order derivative that appears is the first, and so this is a first order differential equation. Now, some of you may have taken Calculus 3 and know about partial derivatives. Partial derivatives are denoted by, let's say, a curved b. It should be written like this, I suppose. This is an old style letter D, kind of style that they might have written in, say, deeds in the early 19th century. For instance, on my great-great-great-grandfather's land deed, it refers to the land, the D being a stylized curved D, very much like that is used to denote partial derivatives. You are not required to know about partial derivatives in this course, and we are not going to talk about partial differential equations. This course is a prerequisite to a discussion of partial differential equations. There are many partial differential equations that are very important in physical applications. For instance, I might have some constant times the partial derivative of p with respect to t equals the second order derivative of p with respect to x plus the second order of p with derivative of p with respect to y plus the second order partial derivative of p with respect to z. This is the famous heat equation. And it obviously has important applications, especially with respect to processes that involve diffusion, or in other words, conduction of heat. But we're not going to make a specific study of this kind of equation here. These equations are very important, but they require the subject that you're currently studying. So, equations involving partial derivatives are called partial differential equations, and we denote that by PDEs. And this course is not about PDEs, it's about equations that involve ordinary derivatives, derivatives of functions that have only one independent variable. Ordinary differential equations are denoted by ODE. This course is a study in ordinary differential equations, or ODEs. Among the most important classes of differential equations that we are going to study are the linear equations. A differential equation is called linear if it may be expressed by an arbitrary function of x times the nth order derivative of the unknown function y. A superscript in parentheses means that many derivatives, plus maybe another function of x times the next lowest derivative on the unknown function y, plus some function of x times the unknown function equaling some arbitrary function f of x. Keep in mind that y and its derivatives appear in separate terms. Terms are separated by a plus or a minus. And in each of those terms, the unknown function or its derivative, one of its derivatives, appears once in the numerator multiplied by an arbitrary function of x. Whatever that function is unimportant. It could be some other function, any old function. For example, let's suppose I have e to the x squared y double prime plus natural log of the absolute value of x times y prime plus cosecant of x times y equals 0. Such an equation is linear. Y and its derivatives appear in separate terms in the numerator to the power 1. Those are linear differential equations. Now, we're going to introduce a word which will have two distinct meanings depending upon the context. All mathematical notation and terminology is conventional. Conventional knowledge is knowledge that is based on an arbitrary choice. It might seem that arbitrary choices are unnecessary, but indeed they can be quite helpful. As an example, let me ask you, what is the color blue? You can point at the sky, you can point at the sea. There are many examples of things that you can point at that are the color blue. There are blue jeans, there are kind of shirts that are colored blue. I point out to my students all the time different examples of the color blue. Well, if there are all these different colors that are blue, what is it that makes the distinction between blue and other colors? Well, it turns out that there are infinitely many possible colors, all possible wavelengths of the light spectrum. And since there are an infinite number of possible colors, but only a finite number of color names, that means that we have to make arbitrary choices as to where the color cutoffs are. We define different color boundaries, blue, green, orange, red, yellow, etc. And these choices are arbitrary, but they're meaningful. They allow us to convey a certain idea. Now, that idea may change across cultures or across times, but that's okay, as long as we're conveying something meaningful to the person who is receiving that information. The same is true about all mathematical notation. All mathematical notation is conventional, which means you cannot deduce it. It's not possible to deduce the meaning of mathematical notation. It is by an arbitrary choice, and that is why you're there and I'm here. I'm here to teach you about those conventions that you cannot deduce no matter how hard you try. But those choices of notation and terminology are still very meaningful, as you'll see as you go on. Now, the word that we're talking about is the word homogeneous. A linear differential equation is called homogeneous. Now, I've had friends who call this word homogeneous, but you don't homogenize differential equations, you homogenize milk. This is the word homogeneous, or sometimes homogeneous. Both of those are correct pronunciations. A differential equation, a linear differential equation, is homogeneous if it has the form just like before. We have arbitrary function of x times derivatives, and we have y and its derivatives in separate terms with different arbitrary functions of x in front of it. But the distinction between a homogeneous linear differential equation and a non-homogeneous differential equation is that here the right-hand side f of x is identically equal to 0. When I write an equal with a triple equal sign, it means it's equal for all replacements of the variable. So this means that f of x equals 0 for all x. And in particular, the left-hand side from before is just equal to 0. So, for example, the differential equation y double prime plus 5y prime plus 6y equals 0 is homogeneous. However, the equation y double prime plus 5y prime plus 6y equals e to the 3x is non-homogeneous. Now, we've talked about differential equations, we've talked about linear differential equations, but we really haven't talked about what it means for a function to be a solution to a differential equation. A solution to a differential equation is a function that, when substituted for the unknown function, yields an identity. So, let me give you an example. We already know that any function of the form c e to the kt is a solution to the differential equation dp dt equals kp. So let's try the following example. 3 e to the kt. Now, in this case, because of the chain rule, dp dt is going to be 3k e to the kt. Now, because of the commutative law of multiplication and the associative law of multiplication, we can rewrite this as k times 3 e to the kt, which happens to be k times the original function p. So we see that kp is k 3 e to the kt, and dp dt is 3k e to the kt. These two are equal for all replacements of the variable t, and hence we have achieved an identity. Therefore, the function 3 e to the kt is a solution to the differential equation dp dt equals kp. As another example, I'd like to consider the equation y double prime plus 2 over xy prime plus y equals 0. I got this example from the Los Alamos primer, and this arises in connection, or something similar to this, arises in connection with the diffusion of neutrons through a critical mass, but it also arises in connection to any kind of diffusive phenomenon. For instance, it arises in connection to the diffusion of blue light through the atmosphere and explains why the sky is blue. So it is an interesting equation to study, but I'd like to make the claim that sine of x divided by x is a solution. But before checking this, I want to introduce a notation. I'm going to say s instead of sine of x, a little shorthand notation, and capital C instead of cosine of x. I got this notation when studying a book by Barrett O'Neill titled The Geometry of Kerr Black Holes. And if it's good enough for studying Kerr black holes, it's good enough for us. By the way, Kerr black holes are rotating black holes. It's what happens to a rotating star when it collapses and forms a black hole. So that would be, well, most of them, I guess. And it turns out in that instance, the star does not collapse to form a point singularity, but rather it collapses and forms what is called a ring singularity. We can talk about that later. In any case, S stands for sine x, C stands for cosine x. So once again, our proposed solution is sine of x divided by x. If that's the case, then y prime can be found using the product rule. Yes, I said product rule. I know that we could use the quotient rule, but I'm going to suppose that I could rewrite this as sine of x times 1 over x. Remember that in the product rule, you take the derivative of the first times the second plus the first times the derivative of the second. In this case, the derivative of sine is cosine times the second factor, which is 1 over x, plus sine times the derivative of 1 over x. But the derivative of 1 over x is negative 1 over x squared. So the second term ends up being minus s divided by x squared. Also, second order derivative, which we need to check to see if this is in fact a solution, can be found by doing the same thing twice, the product rule 2 times. The derivative of cosine is negative sine, and that's still multiplied by 1 over x. And then the derivative of 1 over x is negative 1 over x squared. On the second term, when we take the derivative of the numerator, the derivative of sine is cosine. So we end up with yet another one of these terms. Now the derivative of 1 over x squared is negative 2 divided by x cubed. Negative negative is positive, and so the last term ends up being plus 2 times the sine of x divided by x cubed. To check that the function y equals sine of x over x is a solution requires that we plug all of these into the differential equation and verify that we get an identity. To do that, we'll write this as negative sine over x minus 2 cosine over x squared plus 2 sine over x cubed plus 2 over x times y prime, which is cosine over x minus sine over x squared plus y, which is sine over x. Now, we can simplify this expression by combining like terms. Here we need to distribute the 2 over x, getting a positive 2 times cosine over x squared. Over here we have a negative 2 times cosine over x squared. So this term exactly cancels this term. Similarly, when we distribute the 2 over x here, we get a minus 2 sine over x cubed. Here we get a positive 2 sine over x cubed, and so this term exactly cancels this term. Note that I'm labeling the terms that cancel with each other by these numbers. That way you can look back in your notes and remember what cancels with what. I discovered this method when I was in graduate school taking differential geometry, where there was a large number of terms that had to be canceled, and I realized that if I was ever going to understand my notes, I had to know what canceled with what, and this helped. Finally, you can see that minus sine x over x will exactly cancel positive sine x over x, and so we get something that is identically 0, and we in fact have a solution to the original differential equation. Now, why is this example still up? We said that sine x over x is a solution, but in the same way you can easily show that cosine x over x is also a solution. Here we have two independent solutions to the same second-order linear differential equation. However, one thing I'd like to point out, while these are both solutions, one of them is physical and the other one is not. If this truly represents something involving the diffusion, say, of blue light through the atmosphere or of heat inside of the Earth, then you cannot have infinite values of heat density or of neutron density. And if you take a look, the only place that sine x over x can possibly have a singularity is at x equals 0. But if you take the limit as x goes to 0, sine x over x, what do you get? You can use L'Hopital's rule. L'Hopital's rule says that this will give you the same limit as cosine x divided by 1. And the cosine of 0 is 1. We spent a lot of time in Calculus 1 proving that sine x over x tends to 1 as x tends to 0. Which means that this first solution, it may have a problem at x equals 0, but it's a removable discontinuity. One where if we define the function to be 1 at x equals 0, it's no longer discontinuous. But if you try the same process, let's take the limit as x goes to 0 from the right, cosine x over x, what do you get? The top tends to 1 because the cosine of 0 is 1, but the bottom is getting tinier and tinier. And one very important principle in mathematics is that 1 over tiny is huge. When you divide by tinier and tinier numbers, the fraction becomes bigger and bigger. And this limit is positive infinity. It has an essential singularity. It cannot be removed by just defining the function value to be finite at one particular point. Which means that in terms of physical applications, the second solution, cosine x over x, is physically invalid, not mathematically invalid, physically invalid, because it has an essential singularity. Now, let me introduce some notation. Leibniz used this notation for the derivative with respect to t, the derivative of s with respect to t. But Newton used a slightly different notation for the same expression. Whenever the derivative of a function with respect to time, he denoted that derivative by a dot. So in Newton's notation, if I put two dots over the variable, that means the second order derivative of position, say, with respect to time. Now, I'd like to do an example that involves an experiment that we might perform here in the classroom setting. And it in particular involves something called Newton's law of cooling. Newton's law of cooling says that the rate of change of the temperature of a cooling object is proportional to the difference between the ambient temperature and the temperature of the cooling object. The ambient temperature, say, would be room temperature, whereas the temperature of the object is just that. So for example, if I pull a batch of cookies out of the oven, and if the oven is set at 350 degrees, when I pull those cookies out, they might have a temperature of 350 degrees, but the air temperature might be 72 degrees. So notice that if the temperature of the cookies is 350 degrees and the air temperature is 72 degrees, then this difference will be negative, in which case we're expecting that if the cooling constant K is positive, and we make the conventional adoption that all physical constants are positive, then the rate of change of temperature should be negative. In other words, the cookies should cool. If, on the other hand, the temperature of the cookies is very, very cold, much lower than the ambient temperature of the air, then this difference will be positive, and we may as well call this Newton's law of warming, because the rate of change of temperature will be positive, and the cookies will warm up. Notice also that since this is a differential equation, we're expecting to have an infinite number of solutions. To specify one particular solution, let's assume that the temperature at time t equals 0 is some value t naught. By specifying a differential equation, together with initial data, we have an initial value problem. Or an IVP. We're going to approach the solution to the differential equation in Newton's law of cooling similar to how we approach the Malthusian growth law or the natural growth law. We're going to separate the variables. We're going to do that by multiplying the dt over here and the stuff involving t onto the left. Once we have the differential equation separated in this way, we can integrate to find the solution. On the right-hand side, it's very simple. Kt plus a constant. On the left-hand side, I'd like to review a method from Calculus 1, the substitution of variables. Anytime you have an integral of the form f prime of x divided by f of x, I can solve these equations using the method of substitution. What we'll do is we'll allow u to be f of x, in which case du will be f prime of x dx. The differential equation, the integral, is then transformed as the integral of 1 over u du. I want you to check that yourselves right now. Make sure that you understand where everything went in this substitution, because this is going to be an essential method of integration, as you shall see. Now, on the right-hand side here, we get the natural log of the absolute value of u plus c, and substituting back u equals f of x, we get the natural log of the absolute value of f of x plus c. The solution to an integral of the form f prime of x divided by f of x is the natural log of the absolute value of f of x plus an arbitrary constant of integration. We should never have to do this substitution again, so I want you to study this and make sure that you understand it. Now, in light of the method that we've just illustrated, the variable that we're integrating with respect to on the left-hand side is T. The ambient temperature T sub A is assumed to be some constant, whereas T is a variable. The derivative of the denominator is not 1, it's -1. Now, there's an old Spanish proverb that says, take what you want, then pay for it. And that's exactly what we're going to do. I want a numerator of -1. I'm going to get a numerator of -1, but I'm going to have to pay for it. And the way I'm going to do that is put a negative out front. If I do that, then the integral on the left becomes minus the natural log of the absolute value of TA minus T. The right-hand side is still KT plus C. If we're trying to solve for the temperature T, we need to whittle away at the things surrounding it, starting with the thing that is furthest away by the order of operations agreement. In this case, the thing furthest away from T on this side is the minus. So we need to get rid of the minus. And you always do opposite operations. So if I'm multiplying by -1, I need to divide by -1 or equivalently multiply by -1. So the solution to the differential equation now becomes the log of the absolute value of the ambient temperature minus the temperature of the cooling object is minus KT plus C. And I want you to keep in mind, I multiplied this whole side by a -1. But if I multiply an arbitrary constant by -1, the negative can be absorbed into the C, and that's exactly what we're doing. Anytime you have a constant multiplied by an arbitrary constant, you can replace that with another arbitrary constant. So now, the next step is to get rid of the natural log. To do that, we need to exponentiate both sides of the equation. That gives us the absolute value of the ambient temperature minus the temperature of the object is an arbitrary positive constant times e to the minus kt, where in this case c is an arbitrary positive constant that replaces e to the power of c, which is technically what it should be. Again, we're playing fast and loose with those constants of integration. Now, we need to get rid of the absolute value. To do that, we get a plus or minus. So the ambient temperature minus the temperature of the cooling object is plus or minus C, which I'm going to replace by an arbitrary constant C, not an arbitrary positive constant, but an arbitrary constant now, times e to the minus kt. And this gives us a one-parameter family of solutions to the original differential equation. Solving for t, we can move t to the right and this entire term to the left, yielding t is the ambient temperature TA. I'm going to write this as plus, even though when it comes over it should be minus. The minus can be absorbed into the constant of integration, e to the minus kt. Now, we had another fact. The temperature at time 0 was T0, some value at time 0. T0, if this represents the cookies coming out of the oven, T0 would be 350 degrees, the temperature of the cookies as you took them out of the oven. When I say naught, I'm saying naught as in N-A-U-G-H-T, like it is all for naught. It's all for nothing. And so that's the reason we call this T0. 0 is nothing. The temperature at time t equals 0. Using this equation, T0 will be what you get when you substitute 0 in for t here. That's going to be the ambient temperature plus c times e to the 0. But e to the 0 is 1. And so we get the ambient temperature plus c. It follows then that the constant of integration is the initial temperature T0 minus the ambient temperature, T sub A. We see then that the temperature of the cooling object is equal to the ambient temperature plus the initial temperature minus the ambient temperature times e to the minus kT. Note that as t goes to infinity, since k is positive, this exponential function is a model for exponential decay, and hence will tend to 0. If t goes to infinity, this goes to 0, this whole term disappears, and the temperature at time t equals infinity will be the ambient temperature. In other words, when you take the cookies out of the oven, as time goes on, the temperature of those cookies will approach the temperature of the room, the ambient temperature of the room. Notice also that the constant of integration has some kind of physical significance. In this case, our constant ended up being the initial temperature minus the ambient temperature. That's normally the case. In differential equations, the constant of integration has some kind of physical significance which can only be determined by some data. Now, we're going to perform an experiment, but to get this experiment off the ground, I want to solve something first. I want to figure out how to find the cooling constant K. And to do that, we're going to solve for K by first moving the ambient temperature over, then T0 minus TA is multiplied, so we need to divide that to the other side. Next, we need to eliminate the exponential function e. The opposite of the exponential function is the natural log. So we take the natural log of both sides. That gives the natural log of T minus TA over T0 minus TA equals minus KT. Finally, to solve for K, we divide both sides by negative T. So we get K is negative 1 over T times the log of T minus TA divided by T0 minus TA. We can use this formula for calculating the cooling constant in an experiment that we are about to perform. This may be the one time in a math class that you see a physical experiment performed. I have here a garden thermometer. I know, not a very accurate temperature measurement device, but nonetheless, it'll do for what we intend to do today. And I also have here a can of dust remover. Now, you're not supposed to spray this on yourself like that. When you do, it releases a super cold stream. Right now, this reads about 69 or 70 degrees. That's the current room temperature. How cold will it be if I spray the contents of this compressed gas can onto the bimetallic coil? How low do you suppose that I can drop the temperature? Make a guess. We'll see if you're right. There's a little bimetallic coil, and that is used to measure the temperature. What we'll do is we'll spray this sufficient amount into the back of the thermometer. And as you can see, that temperature drops way below minus 60 degrees. Way below. And it slowly will stop, and then the temperature will start to rise. Now the thing is, there's still a little bit of ice on the bimetallic coil. And so I like to blow on that to get rid of some of that ice. I performed this experiment and every 10 seconds took temperature readings. And I recorded those readings in a spreadsheet. So I'd like you to see that data And I'd like to analyze that. Try to measure the cooling constant K for the bimetallic coil on this thermometer, and then see how well Newton's law of cooling, in this case Newton's law of warming, matches what we observe with a garden thermometer like this. The times are down the first column, starting at T equals 0, where I measured the temperature at negative 27 degrees Fahrenheit, and every 10 seconds thereafter until I got to 140 seconds. We need to estimate the cooling constant K. Remember that the formula was -1 divided by the time times the natural log of the temperature minus the ambient temperature, which we'll take to be 72, divided by the initial temperature, which we'll take here. That needs to be an absolute reference, so I'm going to put dollar signs around that, minus the ambient temperature, which was 72. This gives us an estimate then for the cooling constant, but there are different estimates at different times. So we have all these different estimates for the cooling constant K. What we'll do is we'll take the average of these and use that as our best estimate for the cooling constant. There are certain predicted values that we can make then using our solution to the differential equation. The predicted values were given by the ambient temperature plus the initial temperature minus the ambient temperature, and again we need to make B2 an absolute reference, times e to the power of, and in Excel to do e to the power of you need to use the exp function, minus K, the cooling constant K, which also needs to be an absolute reference, times the current time. We can predict the temperatures at various times using the formula that we found for the solution. Now, what we'll do is we'll plot all of these three together. So we'll insert a graph, a chart, one of these kinds, and you can see that we have a pretty close relationship between the predicted values given in orange and the actual data values given in blue. That's a pretty remarkable correspondence given the crudeness of the measuring device that we used. The point not being that we're going to accurately measure temperatures using a garden thermometer, but the point to see that even with a crude device like a garden thermometer, our theory is accurately matching what we're predicting, what we're observing. I hope you can see that differential equations is about the real world. Almost all physical laws can be expressed as a differential equation in some way or another. I'm excited about studying this topic with you, and I hope you'll continue to join me. Thank you.